In today's lesson, we're going to explore some simple electric circuits. Circuits can be found in every corner of your house, but how do they work, and what tools do engineers use to design them? Engineers use pictures called circuit diagrams to visualize electric circuits. This diagram shows a simple circuit in which a battery provides a potential that drives an electric current through a resistor. Recall that Ohm's law relates the important circuit properties potential, current, and resistance. The potential drop across a resistor is equal to the current flowing through that resistor times the value of the resistor. This water experiment provides an analogy where we can better visualize potential, current, and resistance in a circuit. Here, electric potential is related to the height of the water. The water starts at the top in the funnel and drops 18 inches to the flask at the bottom. This is a potential drop of 18 inches. Electric current is related to the flow of the water through this circuit. We start with 100 milliliters of water at the top, and it all drains to the bottom in 20 seconds. This is a current of 5 milliliters per second. The resistance is related to the number of loops. The more loops you have, the more resistance. Now let's look at potential, current, and resistance in an electric circuit. Our battery provides 9 volts of potential to drive current through a resistor of 1500 ohms. Pause this video and try using Ohm's law in these circuit parameters to calculate the current. When you come back, we'll measure it using a meter. Engineers use a tool called a digital multimeter to measure current and potential in electric circuits. To measure current, the meter must be set up in current mode. This means placing the red lead into the current slot and turning the dial to A for amps. Let's look at our circuit diagram to see where the meter goes. In order to measure current, you must first break the circuit and place the meter such that the current flows from the battery through the meter and then through your resistor. The meter shows that the current is 0.005 amps. How does this compare to your calculated value from Ohm's law? It should be pretty close. To measure potential using a digital multimeter, the meter must be set up in potential mode. This means moving the red lead to the potential slot and turning the knob to V for volts. Let's look at our circuit diagram to see where the meter goes. When we measure potential, we must measure it across a circuit element. This means placing the red lead of the meter on one side of the element and the black lead on the other. Our meter shows that the potential drop across our resistor is 8.93 volts. This is very close to the battery potential of 9 volts. Let's move on to explore some more complicated circuits. Series circuits consist of elements that appear one after another, where parallel circuits, elements appear side by side. Let's investigate how potential and current properties differ between these two circuit types. The diagram on the left represents a series circuit where a battery supplies current that flows through two resistors placed one after another. On the right are the series circuit properties. The first talks about potential. The potential supplied by the battery must drop over the sum of the two resistors, part over the first and the remainder over the second. The second property talks about current. Current flows through each resistor, one after the other. That means the same current that flows through the first resistor must flow through the second. The total resistance in a series circuit is the sum of the two resistances. Let's return to our water experiment so we can better understand potential and current in a series circuit. Water starts in the funnel at the top and must travel through each of the loops on the way to the bottom, one after the other. Notice that there's two distinct potential drops in this circuit, from 28 to 14 inches across the first set of loops and from 14 to 0 inches across the second set, for a total potential drop of 28 inches. 100 milliliters of water starts at the top, and it all drains to the flask at the bottom in 25 seconds, a current of 4 milliliters per second. The water experiences more resistance in this circuit, therefore the current is smaller. In our series electric circuit, a 9-volt battery supplies current that flows through two resistors each of 1500 ohms. To measure the current in this circuit, I broke the circuit here and placed the meter within it. Our meter reads 3 milliamps. This is the current within our circuit, and it's the same regardless of where we measure it, because there's only one path for the current to take. I've rearranged the meters to measure potential in the series circuit. This meter reads a potential drop across resistor 1, which is about 4.5 volts. This meter reads a potential drop across resistor 2, which is also 4.5 volts. Add these two values together and you get the battery potential, 9 volts. The diagram on the left represents a parallel circuit where a battery supplies current that flows through two resistors placed side by side. The parallel circuit properties are on the right. The first talks about current. The current supplied by the battery has a choice as it splits between a path through R1 and the path through R2. The second property talks about potential. The potential supplied by the battery is the same potential that drops across R1 and is also the same potential that drops across R2. The total resistance in a parallel circuit is given by this expression and is less than that as seen in a series circuit. Let's return to our water experiment one more time so we can better understand potential and current in a parallel circuit. Water starts in the funnel at the top and can take one of two paths to the flasks at the bottom, either through the left loops or the right loops. Notice that the potential drop is 18 inches, regardless of which path the water takes. We start with 100 milliliters of water at the top, and approximately 50 milliliters ends up in each of the flasks at the bottom. It takes about 12 seconds. This means that the current in each path is about 4 milliliters per second. Adding these together, we get 8 milliliters per second for a total current. You should expect the current to be higher in a parallel circuit. This is because there are two distinct paths for the water to flow. Therefore, the water sees less resistance and is able to flow faster through the circuit. In our parallel electric circuit, a 9-volt battery supplies current that flows through two 1500 ohm resistors placed side by side. To measure the total current in the circuit, I broke it here. The meter reads 12 milliamps. Now to measure the current flowing through R2, I broke the circuit here. This current is 6 milliamps, which is less than the total, because the remainder must flow through R1. I've rearranged the meters to measure potential in a parallel circuit. This meter measures the potential drop across resistor 1 and is about 9 volts. This meter reads the potential drop across R2 and is also 9 volts. Notice that the potential drop across both resistors in the parallel circuit is equal to that of the battery. Now it's your job to keep exploring. Challenge yourself by investigating voltage and current in more complicated circuits, like if you change the values of resistance, or if you add a third resistor, or even if you combine series and parallel circuits to form a big megacircuit.